You've just started a new internship working at the bank. You're going out for dinner to celebrate the new position after your day ends. You walk in, excited for the day ahead, but a little nervous. You arrive at your desk and, to your horror, you find a stack of documents piled high as the ceiling, each containing hundreds of handwritten numbers. Off to the side, you spot a creased yellow sticky note that reads, "All of the numbers must be copied to the online system before you leave." Surely there's no way to digitize all of these hundreds and thousands of numbers in time for your dinner reservation, right? Luckily, you know about artificial intelligence, which is where computers can complete human tasks, like classifying characters on a document as a digit between 0 and 9. Even better, your friends told you about a type of artificial intelligence called machine learning, where a computer can learn to recognize patterns without even needing your help. Conveniently, you remember hearing about the MNIST dataset, a database of 70,000 images of handwritten numbers. This database is already processed to be easy to work with as possible, and would be perfect to train a machine learning model that can classify all of the numbers in the papers on your desk. You turn on your computer and search for the dataset. Very quickly, you discover that it consists of 28 by 28 pixel grayscale images of handwritten numbers, broken into 60,000 for training and 10,000 for testing. And it's very easy to work with on the web. You quickly find a tutorial on how to build a neural network in Python, and you get down to work. First, you have to format the data you'll be working with. Each of the images contains 784 pixels, and each of those pixels has a value between 0, which would be black, and 255, which would be white. Your neural network will be made up of an input layer with one node for each pixel, a hidden processing layer with 10 nodes, and the output layer with a node for each digit. All of the nodes in one layer are connected to all of the nodes in the next layer, so there will be 7,840 connections between the input layer and the hidden layer, and 100 connections between the hidden layer and the output layer. Now that you've built a framework, the next step is to fill it in, creating variables and running data through it in a stage called forwards propagation. This is where you'll take an image and run it through the neural network. The value of each pixel in the image is multiplied by a random weight and has a bias added at each node in the hidden layer, creating a new value. These weights and biases are what bring a neural network to life. The value created by this is then run through an activation function. Without the activation function, this whole model would just be a very complicated linear function. You choose to use the rectified linear unit function, or ReLU. Good choice. In ReLU, any negative value is equal to 0, and any positive value remains as it is. You've finished building up the hidden layer, and you move on to the output layer. It's pretty much the same as the hidden layer, except it uses the activated data from the previous layer, and the weights and biases are different. The big difference, though, arises when you come to the activation function. This time, you choose to use a softmax function, in which each of the values from the previous layer are converted into probabilities of the initial image being each digit in the output layer. It takes the highest of those probabilities and presents that as its guess. You've built your neural network complete with weights, biases, and activation functions. One slight problem: it doesn't work. All it knows is that it can put an image through and get out a number between 0 and 9. But it has no clue what number is the right number, at least not yet. It's time to teach your neural network. You do this through something called backwards propagation. This starts where you figure out how much our prediction was different from the actual answer, or how much error there is. This error is run backwards through the neural network to see how much each weight and bias contributed, so they can be adjusted accordingly. Each variable has a different equation to determine its error, and it's a lot of simple but fancy math. Once you've figured out how much each weight and bias has contributed to your error, you multiply them by the learning rate and you subtract them from the initial weights and biases. You've chosen the learning rate to be a coefficient small enough to allow the function to pinpoint the best possible weights and biases, but not too small that it takes forever to get there. The model is run again from the start, this time using the updated parameters, and your accuracy is slightly higher. You decide to take a break to give the model some time to refine the parameters, and before you know it, the accuracy is high enough to get some work. You run the last document through the database and you sit back. The first day of your internship, and you've already learned so much. You formatted a dataset, created a neural network with an input layer, a hidden layer, and an output layer. You assigned weights and biases to every node, and used 2 different activation functions. You determined the error using backpropagation, you updated the parameters with a learning rate, and you seemingly got an impossible amount of work done, all in time for your dinner reservation. Oh shoot, your reservation! It's in 5 minutes! You pack up and grab your coat, run out, and excited for what tomorrow will bring.